Okay. All right, I know I'm messing around. All right, so, yes, so no Thursday. So let's see if we can get through the rest of these slides here. This is kind of going to be, well, I have a nice little calculation that we're going to work through, okay? Because, right. So what are we trying to do? We are, let's get back to this picture. We're trying to figure out, and so we've got a random network, we're going to randomly, this is very exciting, right? We're going to randomly wire up a network. We're going to have a degree distribution, and then everything else is whatever we like, right? And so you can complicate these things as you want by adding, say, correlations between nodes according to the degree. You can play around with those sorts of things. It's a nice problem. We wrote a paper about that years ago. And that's one of those things where if you add too many features, then you start to just, it gets meaningless. Anyway, we're going to talk about just this basic toy model story. Because it's quite nutritious, and then of course when you go into the real world, you're out with real networks. Okay, so the main story is, and we looked at how to do this through generating functions. We'll tie that up and kind of get into example next. But just to repeat, the idea is we're trying to find what's a randomly selected node. What's the probability that it has n? There's a part of a component of size n, including itself. And again, you can see how this will work with contagion and so on, but this is all structural right now. And there's the underlying thing that's all you really handed is this degree distribution, right? Infinite networks, this is all you, I mean, it's a big thing, but you're given this arbitrary degree distribution, P sub k. So from P sub k, can we determine this? And there's a recursion relation that must hold, and that is, if we randomly select a node, look at its friends, find out how big the subcomponents are that it belongs to, add all of those up, add 1 for the node that we started at, that is going to be this n we're looking for, right? So pi, probability of n, that's what this big circle is. This gets inflated, right? So we're going to take that and inflate it and do one step of recursion. So n is 1 plus the sum of your friends' component sizes. And so these are components, as you run along this edge, you're looking out, right? We're not looking back, right? It's not the whole thing. That wouldn't make sense. We're breaking it apart. And importantly, these are all finite components. That's the only way this math will work, right? So if this went off to an infinite one, things would explode. And we also have a recursion relation for R sub k, right, which is the probability that you hit a node and it has k other friends. Rho sub n will be this piece we're looking for that's going to be really key, is we're going to hit a node that is we're going to run along an edge and lead to a subcomponent of size n. This gets exploded, right? So we're kind of, if you like, just expanding at one step, right? So this circle here is this circle here. Right, we're showing one step, one like looking at its insides a little bit. A stick. Okay, excellent. Yeah. And so that's going to be, we have a probability of hitting a node of size n. Sorry. We have a probability that we're reaching a component of size n. So we have this piece in here, which is probably that node has k other friends. And then we're going to add up all those pieces. Right, those subcomponents, and so it's going to be 1 plus the sum. And the end of the last lecture, we went through some useful results. Right, so that's the basic picture we need to keep in our heads. Right, we went through this result, and somewhat painstakingly, you'll prove it in a simpler way in an assignment. But it's this result again that if we sample from some distribution, that's the number of rolls of a second distribution we're going to sample from. So we sample from U, it gives us some number. Then we go over to a big die that's got V written on it, or U dice with V written on it, and we roll them and add them all up. And we found the generating function for this new variable is the composition of, which is a cool thing, right? So this is the number, the U again, just so you can kind of remember. These are the things where we're actually getting values from, right? The V, and U is the number that we're sampling from, okay? And so that's going to be clearly, I hope, connected to this piece here, right? So R sub k is going to be our u. That's our u, and this will be our v, for example, in that. Did I say the right thing, or did I get them wrong? I said the right thing. Okay. That's going to be our u. This is the number we want to sum. There are our v's. We sum them. Okay, good. You don't have a problem like if you're shelling peas or cutting up beans, like, and you've got one bucket for the thing you want and one bucket for the thing you don't want, right? And halfway through you just swap. And then you mindlessly do it for, you ever do that? Or just me? Okay. The sorting goes wrong. You're still doing it, you know, correctly, you know. It's not randomized, it's just a straight up switch. Silly. Okay, so gets a tarot card. This is a cool thing. So we went through it, pain, 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 concentrate, and yeah, good. Right. Okay, so that's just something we're going to carry around. And we also had that the sum of two variables, right, so w equals u plus v, then that's just the product of the generating function for w is the product of the generating functions. Very nice. Beautiful.